Assalamualaikum and good morning. Today I will teach you about the second order system. Second order system exhibit a wide range of response which must be analyzed and described. For a first order system, varying a single parameter change the speed of response. Meanwhile, for second order system, change in the parameter of a second order system can change the form of the response. For example, a second-order system can display characteristics much like a first-order system, or, depending on component values, display damped or pure oscillations for its transient response. A general second-order system is characterized by the following transfer function: g of s equals to b over s squared plus as plus b. We also can rewrite the above transfer function in the standard form of the second order system, which is basically the closed loop transfer function, as g of s equals to omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Notice that this omega n, we call it a natural frequency, and this zeta, we call it the damping ratio. According to the value of damping ratio zeta, a second order system can be set into one of the four categories. Okay, the first one is undamped, when the system has two imaginary poles. Okay, so I hope all the students still remembers the definition of poles and also the definition of zeros. Okay, so undamped happen when zeta equals to 0. The second category is underdamped, when the system has two complex conjugate poles, okay, and lie in the left half plane, and here the damping ratio is between 0 and 1. The third category is critically damped, when the system has two real but equal poles, okay, two real but equal poles, and lie in the left half plane. This happens when zeta or damping ratio equals to 1. The last one is overdamped response, when the system has two real distinct poles, okay, two real distinct poles, and lie in the left half plane. This happens when damping ratio is greater than 1. Okay, next, given a step input or unit step input where R of S equals to 1 over S, then the system output is given as follow, where C of S equals to R of S times G of S equals to this equation. Okay, then if we take the inverse Laplace transform of C of S, we have the response of, or the equation of C of t, as shown in this slide. Here theta is given by this equation, and omega d in C of t is given by this equation. Okay, next I will introduce you a characteristic equation, where this characteristic equation can be found from the denominator of G of S. Okay, by solving this characteristic equation, we will get two poles, x1 and x2. And how to solve this one is that you can use a simple math, where the equation is minus b plus minus square root of b squared minus 4ac divided by 2a. So I hope you still remember on using that equation. Okay, so going back to this characteristic equation, we have several terms here. Yeah, you actually will get a general term, the real part and also the imaginary part. Okay, so this real part we call it alpha, and then the imaginary part we call it omega d, where here alpha is a damping factor and omega d is the conditional frequency. Okay. Okay, next, this slide clearly shows how the changes of zeta produce different categories of output response C of t. Okay, so here you can see the first column is the condition of a zeta, and then you can see the second column is the characteristic of the poles. Okay, so this poles is the poles of the characteristic equation. Okay, and the last column is the output response C of t. Okay, so let's look one by one. The first row, when zeta is equals to 0, we will get that the poles is at the imaginary. Okay, actually you can prove using the characteristic equation. Where you solve the characteristic equation, you will get two imaginary poles. Okay, and this one we call it undamped response. Okay, this one we call it undamped response. Next, the second row, when zeta is between 0 and 1, if you solve the characteristic equation, you will get two imaginary and real poles. Okay, like this figure. All right, and this one we call it underdamped response. And the third one, when zeta equals to 1, if you solve the characteristic equation, okay, you will get two real poles at the same location. Okay, this is called a critically damped response. All right, and the last one, when zeta is greater than 1, okay, you will get two distinct poles on the real axis. Okay, and this is called the overdamped response. So I hope that you can memorize this table. Okay, next we will discuss about the transient response specifications of the second order system. So there are five types of specifications. The first one is delay time, where time to reach half the final value, where the symbol is TD. The second one is a rise time, time to rise for the pass command. The symbol is TR. The third one is peak time, time to first peak. The symbol is TP. And number 4 is percent of overshoot. The symbol is MP. The last one is settling time, time to settle into bounds. The symbol is TS. Okay, so we go for the detailed definition. The first one, delay time or TD, is the time required for the response to reach half the final value for the first time. Okay. Next, rise time or TR is the time required for the response to rise from 10% of the final value to 90% of the final value. A precise analytical relationship between rise time and damping ratio cannot be found. Okay, so here the definition is actually same like we learned in the first order system. Next, the third specification is a peak time or TP. Is the peak time the peak time is the time required for the response to reach the first peak of the overshoot, which is given by this formula. Okay, besides you use the analysis from the response, you also can use the formula for TP. Okay, so TP is equals to pi divided by omega n square root 1 minus zeta squared. Okay, not like rise time, there is no specific relation between the rise time and the damping ratio, so you cannot use the formula. Next is the percentage of overshoot. Okay, the percentage of overshoot is defined as the maximum peak value of the response curve measured from unity, which is expressed as a percentage of the steady state value. Okay, so the formula is given below, where percentage OS equals to C max at TP minus C final at infinity divided by C final at infinity, which is at steady state. Then you need to multiply with 100 and you will get the percentage of overshoot. Okay, besides that, there is also a relation between the damping ratio and the overshoot as given in this equation. Okay, so the last one is settling time, TS. The settling time is the time required for the response curve to reach and stay within the boundary of 2% of the steady state value. Okay, I think this definition also we have in the first order system. Okay, so the formula, you also can use the formula Ts equals to 4 divided by zeta omega n for 2% criterion. Okay, in order to clearly figure out all the specification at the output response, we use this slide. So here we have the first one is a TD. Okay, so I hope you still remember the definition. Then we have a TR, okay, from 10% to 90%. Then we have a TP, okay, the peak time. Then we have the settling time, okay, 2% in the boundary of 2%, all right. And then we have the definition of MP. Okay, next we go for the exercise number 1. Find the natural frequency and damping ratio for the system with the transfer function as follows. Okay, so there are two terms that exercise 1 asks. The first one is natural frequency and also the damping ratio. Okay, so natural frequency is omega n, damping ratio is zeta. So first you need to convert this G of S into the common second order system. Okay, so after you convert to this template, you can easily find what is omega n and also the zeta. Okay, so omega n is equals to 6 and zeta is equals to 0.35. Okay, next, given the transfer function G of S equals to 100 divided by S squared plus 15S plus 100, then you need to find TS, percentage of overshoot, and also TP. So what is the tips? The tips is to convert first G of S into the standard form of a second order system to get the omega n and also the zeta. After you get the zeta and the omega n, you can use the formula to find TS, percentage of overshoot, and also TP. Okay, so omega n for this G of S is 10 and zeta is 0.75. Okay, so you can easily calculate or put this value in the equation. You will get TS equals to 0.533, percentage of overshoot is 2.838, and TP is 0.475. Alright, that's all for today's lecture. Thank you very much.